Okay, well, first of all, I would like to thank the organizers for this very interesting conference and for the invitation as well. So I'm going to speak about some density estimates for the Landau equation, which is an equation arising from mathematical physics and which describes the velocity of particles in a plasma. So this is a joint work with François Delarue from Nice and Eulalia Nualart from Barcelona. Okay, so before going to the Landau equation, let us make a small detour by the Boltzmann equation, which describes the motion of particles in a gas, and we will be interested in the evolution of a function ftv, which represents the density at a given time of particles having a velocity v in Rn, n being a physical dimension essentially, but the results can be extended to an arbitrary dimensions. We will be interested in the so-called spatially homogeneous case, which means that the density will not depend, the density of speeds will not depend on the position of the particles. And in some sense, the Boltzmann equation, so the evolution of this density, can be described through a collision operator between particles. And we would have this kind of evolution, of parabolic evolution, that is the derivative in time of the density would be equal to this collision operator. And for instance, here, if we consider two particles with velocity v and v prime, okay. Here we assume that the center, the direction omega is between the center of two particles. We have two velocity v and v prime, which are the velocities of the particles before v and v star before the collision. Okay, and v prime and v star prime are the velocities after the collision. And in some sense, what do? You integrate along all the direction possible between the centers of the particles on the sphere. And theta here stands for the angle between v minus v star. So in some sense, on my drawing, it should be something which is in some sense like that, let's say. Okay. And omega. And the Landau equation will be, in some sense, an asymptotic of this Boltzmann equation when the particles slightly touch. That is, when this is actually what happens on the drawing. V minus V star is, in some sense, orthogonal to omega. Okay. So the collisions are assumed to be perfectly elastic. The velocity between particles is exchanged along omega. So this means this conservation laws in some sense. And the Boltzmann equation has many properties. It preserves the mass, the momentum, and the energy. Okay. And in some sense here, b theta is an interaction potential between particles. So this is just to give maybe an idea, or in some sense, under some nice assumption, the collision operators can be split into two operators associated to the particles which acquire velocity when there is a shock, and those who lose velocity. Okay. Also, we will assume reversibility in the sense that the velocity, the converse is also possible. You can go back from v and v star from v prime and v star prime. The Landau equation we will be interested in corresponds to the case of Maxwellian molecules, which mean that two particles at distance r interact in the following way. And also, we will assume that the interaction potential is a negative function. It is implicitly defined, so it's too long here to exactly introduce this potential. But let us emphasize that it is singular in pi over 2. which means pi over 2 corresponds to the situation of this drawing. When the particles slightly touch, there is almost no speed exchange, which corresponds to the so-called plasma, in the sense that the medium is very dense. So, some good rescaling leads, since the splitting of the collision operator is no more allowed, a suitable renormalization of the potential leads to the so-called Landau equation. So for those renormalization, to go from the Boltzmann equation to the Landau equation, I can mention the works by Villani and another one by Méléard and her co-authors. And we will finally introduce the object of our study, which is the Landau equation, which writes in the following way. So we have still the time derivative of the density, and now we have an integral differential operator written in this way, if you want, where LAFFTV is here in divergence form, okay, and you have some diffusive term, diffusion matrix, which is AV minus V star. Here you have FTV star, but you integrate on V star, and you have a gradient of FTV. So at the first sight, this would be in some sense similar to a term which is usual in PDE, so an operator under divergence form. But the main difference and the common point in some sense with Denis' lectures this morning is that you have a non-linear term here. The A depends on F through the integral with respect to all the velocities. So if you keep in mind that F preserves the mass, okay, this means that starting from a density probability, in some sense, you expect that you will preserve a density probability through the time evolution. And in some sense, this means that you integrate the diffusion coefficient A with respect to some density probability. Okay? So in this sense, it is closely related to a Makin-Vlasov-like equation. And here A, the diffusion matrix A, is very specific in the sense that it has the following form. It is coefficient lambda depending on the form of the potential, square modulus of V, and I minus V tensor V divided by V square. So we can rewrite that using pi of V, which is nothing else but yes, so it's kind of projection. It's a projection on the orthogonal of V, okay? And this is a very specific structure which will be relevant and very useful in the following. So since here we have some projection, we have in particular that A, V and V is equal to 0. Since we have a projection, we already see that the matrix A of V itself is degenerate. It cannot be non-degenerate. Okay? However, one of the very specific features of this equation is that once integrated with respect to the law, it will be non-degenerate. Okay? But you need this further step to be in the usual, in some sense, theory for parabolic PDEs. Okay? And here, briefly, you have, in some sense, the same structure that you had in Boltzmann, the sense that you have some symmetry between particles for which you integrate with respect to all the velocities. And as well, here you have the density and you integrate the gradient with respect to all the velocities. So that there is this symmetry. And one of the goals of the talk is how to find a probabilistic interpretation of this equation. Okay, what is the process beneath? And once we have a process beneath, what representation, what realization of this process can we exploit in order to derive two-sided it kernels for this solution? Okay. So we can rewrite in a more usual way, which would be closer to this representation, the generator in the following form, in divergence form, where here A, once again, I integrate my diffusion coefficient with respect to the density of the solution. Same thing for the gradient. Okay, here I have done some integration by part, which gives me a linear contribution with respect to the velocity. Okay, so the solution is assumed to be non-negative, integrable, and with finite energy. That's what we mean by solution. And some results now. The early results concerning this equation go back to the PhD thesis of Villani, who proved that if we had finite mass and energy, starting from a positive solution, then the Landau equation had a unique classical solution for T positive, meaning that for positive T, you had a bounded and smooth solution. So this means that the Landau solution has the same smoothing effects qualitatively as the heat equation in some sense. Okay, so now if we want to go to more quantitative properties, in some works by Villani and de Villette, they prove that if the initial density of velocities was lower bounded by a Gaussian density for a three-dimensional case, or if the entropy of the initial condition was finite, then we add a Gaussian lower bound. And I emphasized as well, since it will be part of the comparison with our results, that here, for fixed T, the constant appearing here depend on T. Okay? And what are the tools to derive those bounds? As in some sense I have mentioned, once integrated with respect to the density law, the diffusion coefficient is uniformly elliptic. Since we have a uniformly elliptic coefficient bounded from below, the lower bound of the diffusion matrix leads, in some sense, quite naturally to a Gaussian lower bound for the density. On the other hand, if you consider naively the form of the matrix A, which was the following one, V2I minus V tensor V divided by V2, okay? You see that if you are quite naive and you do not exploit the projection structure of this, the bound you can have is the following. You have a quadratic growth on the velocity. So it leaves an open question. What could be said about an upper bound? We have a non-degenerate lower bounds, which leads to a Gaussian usual heat kernel. We have a quadratic growth in the velocity for the lower bound of the diffusion matrix. If we consider it bluntly, what could be guessed about an upper bound? So these are the questions we will try to answer, specifying as well the lower bounds obtained by Villani. Okay, so now the first step consists in giving a weak formulation of the Landau equation, weak formulation, which thanks to integration by parts writes in the following way. Okay. It's simply integration by part, and here we once again rewrite the generator. So you have the difference between the argument V and the argument which is integrated. So here we integrate on the right hand side twice. Sure. Anyhow, as we have seen, the Landau equation preserves the mass. Okay, so this means that if you start from a density probability, then at every time t, you have a density probability. So, okay, we have stated the weak formulation, but as a first step, it could be natural to look for flows of probability measures. Okay, and of course, if we find some good flows of probability measures which have density, those flows will give the density associated to those flows will give a weak solution to the Landau equation. Okay. So this is nothing but the integrated version of the first one. And here PT is, in some sense, we are looking for a density, for a measure satisfying this, this equation. And this a flow PT of measure satisfying this relation will be called a measure solution to the Landau equation.
Here is somewhere again this Reynolds tensor as in Dini talk. Are there some?
No, this is no, it's not a Reynolds tensor. I don't think so. It's just a projection. No. There is no direct link with stress. Okay. So how can we find a solution to those equations? So the natural idea consists in introducing a suitable nonlinear martingale problem. Okay, we say that a measure P on the path space is a solution of a martingale problem if for any test function mt phi, which is this object, in some sense we subtract what shouldn't be a martingale is a martingale.
I see the preceding slide. Something I don't understand. Where is the nonlinear operator?
The nonlinear P is in L. In L, P is
something is missing in the definition of L or not?
No. You have V and V star. You have V and V star. So the integral in V star is the nonlinear term. Okay. Here you have you can rewrite that in the following way, in some sense. It's okay. You could write L phi of V Rn. So here you would have a P S dV, and here a PS as well. Okay.
Well, I don't see P, and I don't see the measure.
There is a double integration here. Okay. So this is where the nonlinearity is. Okay. You have an integral with respect to V star as well.
Yes, but in the definition of L.
In L, you have V and V star, V and minus V star, and you integrate it twice. Okay, so if you want to factorize, you can, for instance, define this operator to go to a more familiar, maybe McKean notation, and this would be, with my notation, L phi V V star PS D V star. Okay. So here is the nonlinear term.
So just to be sure to understand, if I want to identify L as a nonlinear operator, I consider the left-hand side as a function of one variable only.
Yes.
And you
integrate.
I substitute. I put somewhere nu as an index of L.
Yes.
And I integrate with respect to the measure nu,
yes.
the right-hand side.
Indeed.
And now nu is PS.
Exactly.
Okay.
Which corresponds naively to right L1 field.
So notice.
Indeed. Okay. So
I would prefer this notation.
Sorry. So do not hesitate if you have questions.
No, thank you.
Okay, so this is exactly what appears here. This is exactly what appears here. Okay, so it should be clearer now. This should be a martingale. Okay, so indeed, this should be a martingale. Okay, so what can be said? Now we want to investigate maybe the covariance structure of this martingale, and this can be easily done simply taking as a test function the identity which will give the cross variation of the martingale. Okay, and once again here, okay, you have the dependence on the law in the cross variation or in the diffusion term, as we had said here. In some sense, recall that here I integrate with respect to the law, and this reflects exactly that. This is the integrated diffusion coefficient with respect of the law of the underlying process. Okay, so how can we realize such a martingale? This is a question. So A is symmetric, A is this matrix. You can take a root, and it will be important. We will choose a specific root with a specific structure noise, and this will be the whole trick. But you have the choice for the root. Okay, and a first trick would consist in appealing to a result of El-Karoui and Méléard, which gives the existence of n independent white noises with covariance measure PT dV star, so that we could indeed represent the martingale. Here we have the cross variation. If we know that there exist such white noises, then these martingale satisfy these covariance structures. Okay, we know. So to show existence of the martingale problem are, as Denis said, fixed point arguments, and so on. So now we can introduce the Landau diffusion, which would write with this martingale. Okay, here I have my martingale, and here once again to go to the Makin-Vlasov framework, I have the dynamic excess of my process, and I subtract its mean. Okay, I subtract its mean, since PS stands for the law of excess. So it's a specific type of Makin-Vlasov interaction. Here they are smooth. Since B is linear in some sense. Okay, so now from Ito's formula, the law P of a process X solving this equation is a solution to the martingale problem. Okay, so we have to give some meaning to this, and in some sense you don't know very well the law itself. Okay, but simply as from the score representation, you can write the expectation from the abstract space omega. When you write the expectation of a random variable x, you can write that it's the integral of x omega dp omega, or use the law. Here we have used the law. So now we will go backward and to introduce a probability space. Here we choose 0, 1, B0, 1, D alpha, in order to have a more a noise that we can more easily handle. Okay, this score representation allows indeed to exchange this white noise with covariance structures involving the law with a usual white noise, in the sense that with this slight trick here, ys has the law of excess. This is what we mean here, but now W here is a white noise having a usual covariance structure d alpha ds. Okay, so it's simply a trick in writing. So existence and uniqueness for these equations have been established by a student of Sylvie Méléard, who proved that indeed if W are n independent white noises with covariance d alpha dt, x0 is the initial solution, then there exists a unique in-law solution xy. So since we are looking for a pair of processes, y is exactly a process which has the same law. Okay, so we have existence and uniqueness. Now to state, and this gives existence of a measure solution to the Landau equation. So now to go from the measure solution to the weak solution, we need some absolute continuity of the law. We need some absolute continuity of the law, and this is usually investigated through the Maillard calculus. This is what they did. Okay, assuming that the initial condition had moments and was not a direct mass, they could establish that the conditional density, so condition with respect to the initial value, was smooth. Existed and was smooth. And of course, you could disintegrate with respect to the initial value of the diffusion and have this representation for the solution of the Landau equation itself. If x0, the initial condition, is the Dirac mass, the only solution is P0. Okay. Once again, the key point in the analysis is the Malevin calculus and the non-degeneracy of the covariance matrix, which is the following one. The integrated diffusion coefficient, integrated once again, recalling that here writing this is equivalent to rewrite the expectation with respect to the law of the process at time s. Okay? So this is equivalent, what I write here, just to make things clear, to, let's say, the expectation of A. I will write Z minus YS, okay, taken at Z equal XS. Knowing that YS has the same law as XS. Okay? So this is really the same kind of structure as those discussed this morning. Okay? Once again, if x0 is not constant, then this matrix is almost surely invertible, whereas if you do not integrate with respect to the law, it is degenerate because it is a projection. Okay? Now, the Landau equation can be viewed as a parabolic PDE with diffusion depending on f. And we can maybe introduce a more familiar diffusion process once we have those the things at hand. In the sense that, okay, now we can realize the Landau equation in the following way, where bar A is once again the integrated coefficient with respect to the law. And here you have the choice of the root. From this dynamics, you can write a particular approach, and it has been successfully shown to converge. This is a work by Fournier. Since here the A, once again, something like that, the bar A is something like that, and you take the root. So you have the choice of the root, and you see that, okay, you are going to substitute YS with the empirical measure associated to the particles. And this will give propagation of chaos. So this is the standard particular approach to the Landau equation, and it has been done by Fournier. Okay? And what the authors before us did, Guérin, Méléard, and Nuallart, proved that if the initial condition was not supported on a line, this is what it means, this condition, then the diffusion matrix was uniformly elliptic, bounded from below, almost surely. Here lambda is, of course, strictly positive. And they derived some upper bound, some lower bound, sorry, almost similar to those of Villani up to additional contributions, but which were not sharp. So after this long introduction, I think we can now go to our contribution, which consists mainly in exploiting the specific geometric structure of the covariance. Okay? We will exploit the fact that A is a projection onto the orthogonal of V bar. Okay? And to do so, we have to do something which could seem at first sight very awkward. Namely, we are dealing with an n-dimensional equation. Okay, so we suppose we recall from the Ito dynamics of the Landau process. Here, B is an n-dimensional Brownian motion. We are dealing with an n-dimensional equation. Okay, so it's very natural. And the key point here consists in extending the dimension of the noise. Okay? So we do not consider n white noise, but a square matrix of white noises. Why? Because we will see that from this square matrix of white noises, we can realize the covariance structure and understand better what is indeed the right noise structure for the Landau equation. In the sense that if now you have a matrix of white noises, okay, here you take the antisymmetric matrix, okay, you take the antisymmetric matrix of white noises, and from the covariance structure, you see that when you apply this random variable to to a given V, its covariance is exactly the diffusion term A of V.
What is the connection between this enlargement matrix and the old vector?
The connection is that in the Landau equation, you see, I start from this operator. Okay? In some sense, I can choose the process that pleases me and which respects the covariance structure. This one is okay. Here I choose an n-dimensional Brownian motion, and I can take my favorite root of square root of bar A. The other possibility consists I only have to match the covariance structure.
I mean the new...
yes, the new matches. Matches the covariance structure. And why do we do that? Because in some sense we will linearize the non-linearity of the Landau equation. Let me make that clear. So the point is that the A of V reads at the covariance of the image of V by an antisymmetric standard Gaussian matrix. Okay? So this will lead to a new equation for the Ito diffusion associated to the Landau equation. So now by uniqueness in law, we can say that the solution of the Landau equation can be represented in the following way. Okay, xt is equal to x0. Here, this is just a normalization. But what is the main advantage of this representation? You see that here you have an affine. You have an affine differential equation. You have an affine differential equation, and what says affine differential equation say that there is some resolvent underneath. Okay? And the resolvent here will be the Brownian motion on the orthogonal group. Why? Because the resolvent which factorizes has the following dynamics. So Zt is, I introduce this dynamic, it's the identity plus 0t dbs, here it's the Stratonovich integral Zs. Recall that dB is the variation of the matrix of antisymmetric Brownian entries. So this is the Lie algebra of the orthogonal group. Here you have a linear equation in Stratonovich with respect to the variation of the Lie algebra. So this is what exactly lifts you to the group.
And before you consider the matrix differential equation?
Yes. This is a matrix differential equation, sure. So dt is exactly the Brownian, the right Brownian on the orthogonal group. Okay. And now we have the variation of the constant, which said that the Ito diffusion for the Landau equation, this is the one, we have uniqueness in law, so okay, this is a possible representation of this equation, and this special one factorizes through the Brownian on the orthogonal group, simply meaning that I can write the solution. It is simply the variation of the constant. It is Zt x0. So this means Zt x0 that your initial condition will be translated by some rotation. Okay, and then you have the integral between 0 and t Zs minus 1. Denis will ask, where has the nonlinearity gone? The answer is the nonlinearity has gone here in d bar b, because d bar b involves the law of the process. Ys is the law of the process. Okay? And the magic thing about this representation is that both b and bar b are, b is defined here. B and bar b are Gaussian processes, and if we assume that the initial condition has zero mean, since the Landau equation preserves the mean, we know that the expectation of yt is 0. So if you compute the covariance between bar b and b, you see that what is left is the integral between 0 and 1 ys alpha d alpha, and this is equal to 0, because the moment is preserved. And since they are Gaussian processes with 0 covariance, they are independent. And this fact allows to obtain a very precise representation of the conditional density of the Landau equation, which writes in the following way. Actually, since we have z is a function of b, bar b is independent of z, okay, well, I will condition with respect to z and obtain an explicit Gaussian-like representation. Gaussian-like representation, okay? And here the covariance matrix is zt zs minus 1, and here I find exactly the expectation of A up to a normalizing, exactly the expectation of A of xs. And now once we have this kind of representation, it is very natural to say, at least at the formal level, that since those processes are rotation processes because they are the Brownian motion on the orthogonal group, the behavior of the covariance matrix will be mainly given by this term. But you can do usual stochastic analysis to derive how it behaves. So once again, the behavior of CT essentially depends on the one of lambda being exactly the expectation of that. So now the proposition is the following: when x0 is not a Dirac mass and is centered, then we have now, and this is a remarkable thing with respect to the previously obtained result, okay, we have a non-degenerate upper bound, lower bound, but as well a non-degenerate upper bound. Non-degenerate, it will depend because the function psi here is the following, okay, is the following. And there is indeed a dichotomy. If lambda is strictly greater than 1, so this means that indeed the initial condition is not distributed along a line. Then we have uniform ellipticity. Okay? And if lambda is equal to 1, we have a new bound. So when the initial condition is distributed along a line, we have a new lower bound which in short times is equivalent to 2n minus 1t. So we have an additional degeneracy. And we have an additional degeneracy. So anyhow, so if we now consider the case when indeed lambda is equal to 1, so in the non-degenerate case, we have that from the uniform ellipticity and boundedness, almost the same behavior as a usual heat kernel. Okay? Be careful anyhow that here you have ZT. ZT is still a rotation process. Okay? Since it is if you are even from now on, if you are interested in giving some integrated estimates for the Landau equation for a given initial position, initial function, you can switch the ZT on ZT star and integrate with respect to x0. So this will, for instance, improve the bounds by Villani, since we see that we have no constant depending on time. Okay, the constants are uniform with respect to time. But now we are tempted to do something more, because ZT is the Brownian motion on the orthogonal groups, and we have heat kernel bounds for that. We have heat kernel bounds for the Brownian motion on the orthogonal groups, which read in the following way. So here you have the volume of the Riemannian ball. Since we are on a compact group, this volume will be homogeneous to a constant after a finite time. And here we also have the usual Riemannian metric. So it reads as a usual heat kernel bound for a compact manifold. Okay, and using this bound, we have some some sharper bounds on the conditional density, which are the following. So it's maybe a bit ugly to read, but I will try to specify things. So let us forget about delta, for instance. Here we have the usual diagonal decay of non-degenerate heat kernel estimates. Okay. Here we have a radial cost and a tangential cost. The radial cost is similar to the one in the Gaussian setting. The tangential cost is different. Is different. Why? Because we would have this in a Gaussian setting. So here there is a 1. So this means that we have a kind of superdiffusivity phenomenon for the Landau equation. Let me specify that. And the correction here is also linked to this superdiffusivity property. Okay, so if x0 and v are both small, let's say that, well, delta t is equal to 1, and we have a usual heat kernel estimate, Gaussian heat kernel estimate. Now, if the infimum is greater than 1, and we are in small time, we have some kind of superdiffusivity, okay? And this means that we have in particular this exponential factor, and as well that the tangential part will vanish. The tangential part will vanish much faster than in the Gaussian regime. Okay? In some sense, recall that we have ZT. ZT means that you quickly average on the unit sphere in some sense. And you will forget the circular distribution much faster than for the usual heat kernels. This is what it means. And here you could wonder why n-1. n-1 comes from the fact that we have disintegrated the spatial orthogonal group as the sphere in dimension n times the spatial orthogonal group in dimension n-1. And this corresponds to a variance, a typical variance for the heat kernel on the sphere, which is a manifold of dimension n-1. Okay? It's a variance contribution for the heat kernel on the sphere. Okay, so now let us say what happens for large t with respect to x0 and uniformly in V. Delta t tends to 1. And we have a Gaussian behavior in long time at a faster rate because of the superdiffusivity. Since we have this relation for the inverse of tangential variances, which means that the Landau variance is much bigger than the usual Gaussian variance. Okay, so this was the picture for the non-degenerate case. Now, what about the degenerate case? So this means that the initial condition is supported on a line, and in that case we have two specific features that appear. The diagonal decay emphasizes an additional singularity, and we have also a mixture of exponential concentration and Gaussian concentration. Okay, so these are the things that appear specifically in this case. So I think I will stop it. Before I will also say that I think that this representation should or could be exploited to derive a particle systems, but a particle system which would involve white noises. And this maybe this appeals to somebody here or some people. I would be glad to discuss about that. I think also that we can consider the spatially inhomogeneous case, which would correspond to adding the dynamics of the position, which would be the integral of the velocity. So I think some things can be done from that. Okay, well, I thank you for your attention.
Questions, comments?
Yes, just concerning the particle system, don't you think that, I mean, the white noise appears in the limit. At the very beginning, there is a collision.
Yes.
Only a collision storm.
Yes.
And then my first reaction would be that what should be simulated is a system of colliding particles. And algorithms like a Landau algorithm for Boltzmann equation could be,
of course,
be adapted for that case.
So this also raises the question of a similar representation for Boltzmann, which is not clear, which is absolutely not clear, because here we really have a very rich structure because of the differential setting, and it's much less clear for me for Boltzmann. But yes, maybe the right approach would be to start with the colliding kernels. Yes, maybe.
If I have time, may I ask a second question? I've not well understood why the miraculous W
Let's go to the miraculous W.
Antisymmetric W appears. So,
it is simply, you have an SDE here. Here you have an SDE. You know that you have uniqueness in law for that. Okay? So you have, what you have at hand, in some sense, is a choice how to realize the noise. You can either take your favorite square root of the diffusion matrix, either, and this is our point of view, realize the covariant structure thanks to a different noise, which has a more appropriate structure. This is why we introduced this noise.
yes, but why this increased dimension helps you?
Because it linearizes the equation. With this noise, I can write the dynamics of my Landau equation in the following way, which is affine, and which was absolutely not before.
Roughly speaking,
It's a way to linearize the equation. This is why we have after that this beautiful representation in some sense. Here you have an affine x, 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 and y. Okay. And then there is a double miracle. Okay, you have a linear equation, and you have independence because the initial law is centered and that the centering property is preserved through the evolution. You have that. Of course, there is still a track of the nonlinearity, which is here, which is exactly here, the nonlinearity. But the miracle is because of the centering, the Gaussian processes are independent. B, okay, B, this is an antisymmetric Brownian motion. It's a Gaussian process. Bar B is also a Gaussian process. Because of the covariant structure, we see that they are independent. And since we have independent processes, now this representation allows me, for instance, to condition with respect to Z, and I have simply a Gaussian density, which writes this way. Okay? So this is the miracle. And which really helps to understand the structure of the equation. So it is indeed an unnatural idea.
Okay, and it's not enough to say that the integral of A of xs dw is white noise, because A depends only on the projective process.
It depends. It's A1 half in dynamics. Which A1 half do you choose? This is the point. You have the choice of the square root. A is linear, of course. Not linear, but quadratic. Okay? But you have the choice of the square root of that And what I pretend is that the introduction of this specific noise structure gives a root which gives a linear equation, which was not the case in the previous choices. And once you have these linear structure, then it is much easier to investigate, and it is the natural representation. It trivializes the Malliavin calculus, since Malliavin calculus in some sense is some integration by part technique. Here it's explicit, since you have a Gaussian representation. And also it really specifies how the tangential effects have to be taken into account.